Hello and welcome. Today, we're diving deep into a world where a mathematical proof and a computer program aren't just kind of similar, they're the exact same thing. It's a wild ride to the very heart of what it means to be certain about anything.
So let's just jump right in with the big question. We rely on incredibly complex math and software for everything, right? From financial markets to sending rockets into space. But all of it is built by humans, and we all know humans make mistakes. So how do we get past just being pretty sure something works to being absolutely 100% certain?
And that question kicks off our first section, the quest for certainty. This isn't a new problem, you know. It's something mathematicians and computer scientists have been wrestling with for a long time.
And think about what's at stake here. You've got a proof that's a million lines long or a software system with countless moving parts. A single forgotten edge case, one tiny misplaced assumption, and the whole thing could come crashing down. The sheer complexity is our biggest enemy, making it almost impossible to check everything by hand. We need a better way.
And that better way comes from a really radical, kind of mind-bending idea. It's an idea that connects the abstract world of pure logic with the very concrete world of computation. The whole thing is built on a foundation called type theory. Now, you might hear type and think about basic programming, but forget all that. This is on another level. Here, a type is a super strict way of classifying information. It makes sure you can't do nonsensical things like add a number to a sentence. And it's this incredibly precise classification that's the key to building systems we can actually verify. And that brings us to the main event, the big breakthrough. It's often called the Curry-Howard isomorphism, and it is just so cool. Get this. The idea is that any logical statement like, for all x, y is true, can be thought of as a type. So what's the proof? The proof is a program that perfectly fits that type. Think of it like a puzzle. The theorem is the empty shape, and the proof is the piece you have to build. If your program, your puzzle piece, fits perfectly without any errors, the proof is valid. And the best part? A computer can check that fit with perfect absolute accuracy.
Okay, so that's the theory. But how do we actually put this into practice? Well, we do it with some very smart software.
A proof assistant is basically the world's most picky, most logical, and most relentless referee. You write out your proof step by step, and this tool checks every single move against the fundamental rules. It doesn't get tired, it can't be fooled, and it will not let a single tiny mistake slip by. It's your guarantee of correctness.
And this idea has led to a whole family of amazing tools over the years. It really started way back in 1968 with a pioneer called Automath, but from there it's evolved into these absolute powerhouses. You've got Coq, which has been used for some of the biggest formal proofs in history. Then there are tools like Ogda, where the line between a programming language and a proof tool just completely blurs. And of course, you've got the workhorses like Isabel/Hull, used to verify the kinds of complex systems that we all rely on.
So, what can we actually do with these things? I mean, what's the real-world impact? Well, the applications are pretty staggering, really. They go from the purely theoretical all the way to the critically practical.
For starters, how about this? Verifying the entire foundation of mathematics itself? Yeah, seriously. Researchers have actually used Coq to formalize the axiomatic set theory that pretty much all of modern math is built on. This gives us this incredible, unprecedented level of confidence that the very bedrock of our logic is solid and free of paradoxes.
And what's so cool is that these tools aren't just for checking old homework. They're actively being used to forge new frontiers in math. People are using them to build bridges between the world of types and the world of abstract shapes, a field called topology. This lets them explore these complex geometric spaces with the same rigor and certainty as code, which is opening up entirely new areas of research.
And finally, it all comes full circle, right back to writing better, safer code. Imagine trying to prove that a massive computer network with thousands of machines all talking to each other will never, ever crash or get stuck. Well, using models like the pi calculus, researchers can now use these type systems to formally guarantee that a program won't get trapped in some infinite loop. This is a huge step towards creating truly unbreakable software.
The pace of innovation in this field is just wild. It's moving incredibly fast, and it's pushing the boundaries of what we even thought was possible in math, logic, and computer science. So, where is this all headed? Well, the cutting edge is exploring some truly mind-bending stuff. I mean, look at these ideas. You have homotype theory, which is basically a whole new foundation for math, where types are treated like geometrical spaces. People are designing frameworks to write provably correct code for quantum computers, and they're even generalizing these ideas to infinite dimensions. The big takeaway here is that this quest for certainty is leading us to fundamentally new ways of thinking about computation, space, and maybe even reality itself.
It all leads to this one final, pretty profound thought. As our world gets more and more complex, are we heading for a future where the creative spark, the innovation, comes from humans, but the absolute ironclad guarantee of correctness is handed over to our perfectly logical machine partners? What a future that would be. Thanks for watching.